So we're working in MINITAB version 19 here, a little bit different to the older versions you might be used to, but not that much different. Session window where information is going to appear, graphs and statistical outputs are going to appear up here. We've got this navigator window that's appeared where lots of the analyses and graphs that we've done are then going to be all stacked up in this navigator window. And then we've got our data and the worksheet window down here. All the other menus up at the top here seem to be fairly similarly organised as they were before. So we'll do a one-way analysis of variance. We've got a data set here then where we've been applying different fertilisers, either no fertiliser, grow fast fertiliser or super plant fertiliser, and been measuring the height of plants. Very simple experiment. So independent variable is the type of fertiliser, of which no fertiliser is a type, and our response, or our dependent variable, is the height of the plant. Simple experiment. Null hypothesis is that there is no significant difference in the height of the plants on the three fertiliser regimes. Let's have a quick look at the data on a box plot first of all, and see what's going on there. So we'll do the height of the plants plotted against the fertiliser. Box plot's useful because it can tell us if there is any outliers in the data. So there's our box plot. We can see then for each one, grow fast, the median, that's the line in the middle of the box plot, is the median. The lower line, this is the interquartile range within this blue box here. So this is the lower quartile and the upper quartile. These whiskers coming away then are the range excluding any outliers. So we can see we've got no outliers in this data because there's no little asterisks above or below any of the box plot. So we've got no outliers as far as a box plot is concerned. We can see that super plant is very much within the error. The median is within the error of no fertiliser at all. So we might then think there is no significant difference between the plant height between super plant and no fertiliser, but maybe the plants have grown significantly higher with the grow fast fertiliser. So because we've got three, well, we're going to check for three means rather than three medians. We need a one-way analysis of variance to do that. Recall, before we do an analysis of variance, we've got to use Levene's test to test for any departure from homoscedasticity. So I'm putting my response in as the height of the plants, the fertilisers, my factors. Notice the language of ANOVA has changed a little bit there. Its factors becomes the independent variable and response becomes the dependent variable. So remember with Levene's test then, we are checking to see if there is equal variances, variance being the scatter about the mean. If those variances are not the same, then that's a big violation to the assumption of the ANOVA. So we're going to use Levene's test here. We can see with Levene's test we get a test statistic 1.31 and a p-value 0.273. We need that p-value from Levene's test to be greater than 0.05. This means we fail to reject the null hypothesis that there is no significant difference between the variances. Be careful on the tricksy double negatives there. Say it again. Our null hypothesis here is that there is no significant difference between these three variances. That's a null hypothesis which we fail to reject. So that's what we need. In order to run the ANOVA, we want this Levene's p-value to be greater than 0.05, which it is here. So I'm going to go in and do the ANOVA and do it through this general linear model window. Notice we can also do a one-way ANOVA up there, but because we're likely to have a more complex experimental design, we'll do it through this later on, more complex experimental design. We'll do it through this fit general linear model option. So the response was the height of the plant, the factors. So the response was the height of the plant, the factors is fertiliser. Remember, we need to store the residuals. Another important check on the assumptions of the ANOVA. We don't need each individual factor to have a normally distributed height. If there's departure from normality in the heights themselves across across the factors, that's not too much of an issue. But the error terms need to be normally distributed, especially when the sample size is low in the ANOVA. So we're going to store that result there. So there's the residuals have appeared. How much each observation, so we can see here how much this 23 is 4.5. Doesn't give me the height units, that's a bit naughty, isn't it? But it's 4.5 of whatever those height units are, centimetres, millimetres, kilometres, whatever it is. 4.58 units higher than the mean for no fertiliser. This one, row 4, is at 17 height units, which is minus 1.42 height units lower than the group mean. This one then, at row 6, is much lower than the group mean. The null hypothesis of this analysis of variance is that there is no significant difference between these three means. We have rejected that null hypothesis. Look at the p-value. It is not resolved at 3 decimal places. I could increase the decimal places. Let's see if it's resolved at 16 decimal places. Yes, it is. But that's such a tiny p-value, we're not really interested in it being that small. The fact is, it's less than 3 decimal places. So we would write this as p equals, if I put it in here, p is less than 0.001 is how we would write it. If we're being really properly pedantic, we would say p is less than 0.004. Sorry, there we go. But that's being ridiculously pedantic. If p is less than 0.001, then we are happy. Is r squared telling me the proportion of the variability in plant height that is explained by variability in the 3 different fertilizers. And we've got just about a quarter of the variability. So there's quite a bit more going on in this data. There's quite a bit of variability in those plant height within the plant heights within each factor as well as between factors. So we still have not yet got our significance, our post hoc test to tell us which fertilizer is significantly different from which. Before we do that, we'll just check the residuals for normality in the usual way. Basic statistics, graphical summary of the residuals, and I'm needing that Anderson-Darling p value to be greater than 0.05, which it is. So I can see my p-value here, 0.569. On the histogram, looking nice and close to a normal distribution. My skewness and kurtosis are both low. So I've got, and most importantly, my Anderson-Darling normality test p-value does not allow me to reject my null hypothesis that the data distribution is not significantly different from the normal. So I just need to finish off with the post hoc tests then. So I go into the ANOVA menu, general linear model. All these that were grayed out before, which I couldn't do, I can now do because I've fitted the model. So I go into comparisons. Fertilizer is my term. I could then ask for just the grouping information, which this gives me the Tukey groupings, the A, B, C groups, where means that do not share a letter are significantly different. I could also then ask for tests and confidence intervals, where I get the p-value given to me against the null hypothesis that there is no significant difference in the plant height, mean plant height with the no fertilizer group compared to the mean plant height in one of the other fertilizer groups, whose name I've forgotten right now. So what we can see, as we sort of inferred from the box plot before, none and superplant don't seem to be that different, and against the comparisons we can see none and superplant both share the letter B. Means that do not share a letter are significantly different. So its grow fast has a significantly higher plant height. You can see the benefit of this navigator menu allowing me to flip between all the different stages that I've all the different analyses that I've done. Here's my 2 p-values against none versus grow fast. The p-value that they're not significantly different is less than 0.001. Reject the null. Superplant and grow fast, reject the null. Superplant and none, no significant difference. So to finish off then, because we've analysed means, it would be a bit, be a bit of a disparity between talking about significant differences in means, but then my box plot is of course displaying medians. That's what this line is in the middle. So it would be better to go into graphs, and if I was wanting this to go into a report, I would put my height as the graph variable, my fertiliser goes in there. And then I'm going to need to do some polishing on this graph here, aren't I? Now that's a much more useful there. So I could then start adding my A's and B's. If I could just see the pesky text box wherever that's gone. Where is? I can't see. There should be the function to add a text box, but I can't see it. I'll find that on another one. Or we could just do this in the graph. We could do some post-production of the graph in some different software. I could add my interval plot of height. I've clearly got to do some, edit the graph. There we go. So I'll put in an A there. And and I'm going to put a B there. And another B and go there. I now need to copy that text across saying means that do not share a letter are significantly different, etc. And just start polishing up this graph. Some height units need to go in. That fertilizer could possibly disappear because it's fairly self-explanatory. The title needs some work as well. So you can just see by clicking on things, I can then be adding units and getting my graph ready to go into a report. There we go.